Uh, Good afternoon, everyone. So let's start the session in the afternoon. My name is Chen Hui Du. You can also call me Rita. I'm assistant professor at Georgia Tech, working on quantum sensing of quantum material using nitrogen vacuum center based color centers. This afternoon, we will have several talks, and usually is 20 minutes talk with 10 minutes questions. So I will give sign around 50 minutes. So you will start to wrap up. So first speaker is Andrea Damascelli at UBC, and he will talk about from adatom-induced superconductivity to strain-induced Landau levels in graphene.
Thank you. Thanks so much. Good afternoon, everyone. Thanks for coming back, and thanks to the organizer, of course, for inviting me to be here. It's a great pleasure to be here. It's the first time at Rice University, and after, I think, 3 times that we have between UBC and QMI, in particular our institute, and the Rice Center for Quantum Materials, a workshop, a yearly workshop. And the first one has been at UBC, so the Rice crowd could come over and visit, and all of the other ones have been remote, so I've never been here. So finally, finally I can be here. So thanks so much. The work I'll be showing today has been done at UBC in Quantum Matter Institute. It's our equivalent that you have here. An important part is also the collaboration with Max Planck in Tokyo under the aegis of the Max Planck UBC Tokyo Center for Quantum Materials. And you're going to see there are collaborators from both sides. Today I'll talk about graphene. And in particular, I'm looking at 2 ways of engineering electronic structure in graphene. One is through a substrate, and one is through atoms that you put on the surface in UHD. So, of course, the topic is the one of band engineering. But again, the key difference between what I will talk about and what we've seen so far, we are now able, so far in what we've done, using angle resolved photonic spectroscopy to look at the electronic structure of this system just by twisting different atomic layers. And so what we do, we work on graphene on silicon carbide. So we have an interaction with the substrate, which is very important. And so then we use either the substrate from below or the top surface of the interface with vacuum by putting atoms as a way to create either flat bands or other physical phenomena. I like to start from superconductivity. So this is the first thing we did. And in this case, we followed a proposal by an Italian group, Profeta in particular, and collaborators, who look at the idea of having graphene, whether freestanding or whether on silicon carbide, and then grow a superstructure of lithium atoms on top of it, and use that to modify the electron phonon coupling in the system and induce superconductivity. The theoretical study look at doing either with lithium or calcium. Turns out that lithium is more effective when it comes as an adatom and a superstructure on the surface. The effect is that really of inducing electron phonon coupling, and the predicted phenomenon would have been superconductivity with TC of 8 Kelvin. So quite remarkable, larger than in the intercalated systems. Here, what you can look at is the alpha squared F of omega. So this is the Diasberg function, basically, is the phonodensity of state, but weighted by the electron phonon coupling strength. And what this graph shows is a function of frequencies. For 2 systems, in black you have the one for a bulk lithium intercalated graphite, or graphene, graphite. And the other one is a monolayer graphene in red, where now lithium is on the surface. And what you can see here, you can see that you have strong modification of the phonon spectrum, again, weighted by the coupling strength in the low energy range, and that's where it's coming from lithium atoms and so on. And now you can calculate the electron phonon coupling lambda as an integral of this quantity, the integral of the alpha squared F function. And you can see that for the bulk system, you have a lambda 0.3. However, you can take it to a lambda 0.6 once you have a well-defined superstructure on the surface. And that should be enough to induce superconductivity. So that's the idea that we followed back then. And as we do, we start off with our graphene sample. The graphene sample so happens to have a Dirac point which is below the chemical potential because it's actually endo through the substrate. We then deposit lithium on the surface, about 3 minutes of lithium deposition. That, of course, is a challenge to establish how much lithium has gone on it. And you can see that the chemical potential drops down, the Fermi surface gets large. You now get these large Fermi surfaces at the K prime points. And at one point, you can quantify the amount of carrier density you have induced in this system. And this is plotted here as a function of the lithium deposition time in minutes. And you can see that we can dose the system, and then we reach a saturation point where we no longer are able to put electrons into the system. Together with the enhancement or enlargement of the Fermi surface, we also get a folding of bands at the gamma point and also a lithium band in this particular case of heavy doping. And I'll come back to that towards the end of the talk. Now, the question is, what can we say about electron-phonon coupling? So here you see now the dispersion of the Dirac point. It should be a linear dispersion. You see an anomaly here, which become more obvious once we plot the maxima of the dispersion versus a linear band. But basically here, what you're seeing is really the spectral function as measured by photon emission, spectral function that can be described in terms of an imaginary part as well as a linear part. The linear part describes the deviation of a pole structure from the perturbed system, and the imaginary part gives you the line width. And you can see there is a finite line width in this spectra. This is the lifetime. And there is the structure here, which is capturing the real part of the self-energy. Now, at the top, we plot the dispersion. So in orange here, the position of the maxima in that dispersion as compared to a linear dispersion you would expect. You can then, from the difference, extract the real part of the self-energy. And now the interesting part is to go and invert this relation that puts, in direct relation the self-energy with the alpha squared F function. And you can invert this relation using a maximum entropy method. And what you have here now is the alpha squared F versus energy, here in red, orange, as extracted through this analysis of a self-energy. And then, of course, by an integral, you can look at the electron-phonon coupling lambda. This is now the first curve you see here is for a 3-minute lithium evaporation. Now we're going to see what happens when we change. We go from 3 to 6, and you see an enhancement of the self-energy, enhancement of the lambda as well. And finally, we go to 10 minutes lithium deposition. And now we have the lambda we obtain actually can be compared very well to the one that was predicted by Profeta and collaborators, and is reaching that value of 0.6 that supposedly is the one that gives us superconductivity. And so the question is it observable? Can we see it in the spectrum? The way we look at superconductivity when it comes to angular result for emission spectroscopy is to look at the density of state right of the chemical potential. If we had a metal, like shown here, constant density of state, chemical potential right here, you have electrons occupying the states below and nothing above the Fermi function. Of course, at 0 temperature, this would be a sharp discontinuity. At finite temperature here, 2 curves, 15 Kelvin or 3.5. The finite discontinuity is no longer finite, has a width. The width is the result of energy resolutions and temperature, finite temperature. But what you can see cooling down is that when you go to 3.5 Kelvin, the spectra gets sharper. However, they cross right at the chemical potential. So this is a typical behavior for a metal. On a superconductor, oopsie, sorry, wrong way. What you would see is that you would see a change of the density of state where you have a gap now, the pairing gap, and you have a pi-lapo density of state below and above the gap. Now, photon emission can measure below the gap, and what you see here is now similar curves, but however, the blue curve down at 4.5 Kelvin, and this is niobium, superconducting niobium, is actually pushed back as the leading edge, which is pushed back with respect to the Fermi function. And that pushing back directly tells you that there is some pairing going on. And you also have an increase of density of state below. Again, these are affected by resolution effects. The gaps are very small, TC is small. But if you take this data and you symmetrize, you can produce a curve which is similar to an STM-like spectrum. And you can see that between the above TC and below TC, there is this suppression of density of state, which is directly your superconducting gap, or proportional to that, let's say. Now, the question is, can you do it on this lithium decorated graphene? We do the experiment, 15 Kelvin, 3.5 Kelvin. So in blue, you see a little bit of a pi-lapo density of state, very small, of course, and a little bit of more evident is the pushback of the leading edge. And again, if you do a symmetrization of the data, you see a small suppression right at the chemical potential at the lowest possible temperature. So from these, we can actually conclude that we have a spectroscopic evidence for a gap. The gap, if we look at the 2 delta, is 1.8 MeV. The lambda is what you would have expected from just having enhanced your electron-phonon coupling with lithium deposition. And if we were then to, and so there is no other mechanism like CDW and so on that would justify a gap of that kind, temperature dependent. And so from this, we take it as evidence for superconductivity spectroscopically, at least. And if we look at a BCS relation, we infer a TC of the order of 6 Kelvin in this system. Now, this is all for the superconducting part down through the surface. Now, the question is, can you now take it more into the flat band? And here I really mean flat bands. And the flat band I would like to go for are Landau level-like flat band. The challenge, though, is that in photo emission, you can't really put a field. And so we couldn't study that way, at least. Well, Ming-Chi is doing some of this work now with fields in photo emission, but it's very challenging. And the question is, how large a field would you need to do that? And so here we try to do that through pseudomagnetic fields, so using strain as a way to induce Landau level in your system. And the idea comes from the fact that we, on graphene, this is Guinea's work, very well-known work, where if you have a distortion of a proper symmetry, you can actually induce a pseudo field in your system, which can be as large as 300 Tesla, as seen by Micromis group in graphene nanobubbles. Can we do that? And well, so here are our samples. Here you can see terraces on a silicon carbide system. This is due to the misfit, but the terraces. More interesting are the features, the small triangular features you see there on those terraces. I can zoom into those. This is an STM image you're looking at. And on this system, we have these triangular trenches, which correspond to a missing silicon carbide layer onto your system. So now you have a sample or a substrate, which has this missing top layer in this triangular object. And what is critical is the stacking of the different layers that now gives you a different registry for the layer below as compared to the very top one. So now if you look at a system like this, there's now graphene on this material, a one monolayer uniformly covering all of the trenches as well. You start seeing, I'm not sure if the screen now allows you to see them, some features which are more prominent as flat, high intensity regions. If you integrate the spectra here in the middle, you can see now there are some free features also there. More evident becomes when you do a second derivative of the data. In addition to the Dirac cone, you see these flat terraces of intensities, and you can clearly see three of them. And now what is key here is to look at the energy evolution of these features. And so you can plot the binding energies of those flat levels, and you can see that they go as square root of n. So basically, this is the typical dependence you would have in a system if a Landau level structure is established. A couple of points to be made. One is, here you see Landau level 1, 2, 3. We heard from Rachel's talk earlier today, that the zero Landau level would be strongly protected. We don't really see that in the spectra, and so I'll come to that later. The other one is to realize that, if we want to have a pseudomagnetic field being responsible for this, you have to have strong enough splitting of these levels compared to the thermal energies. These are actually seen at low temperature as well as all the way to room temperatures. You have to have a lifetime for the carrier, which is larger than the typical time of an orbit around a cyclotron orbit. And then more importantly, also the region of space on which you have a uniform field or pseudo field has to be large compared to the magnetic length, so the size of an orbit itself. So we can go and model this system to really see if it's consistent with the interpretation. What we see here is the energy distribution of these Landau levels as a function of n, so square root of n, with respect to the Dirac point. And in fact, if we use this particular relation, we can, from the data, tell that the field, the pseudo field we have generated, is of the order of 40 Tesla. So now the modeling takes a flake, a triangular flake of graphene, is looking at distortions of it, which would modulate the hopping parameters in the system. And this is work done by Marcel Franz and collaborator at UBC. And what they're able to do quantitatively is to look at a 56 nanometer flake or say triangle and impose a 3% strain. And in that way, they're able to generate a 41 Tesla field and a uniform area for the field of 30 nanometers to be compared with a magnetic length of 4 nanometers. And this you see up here is the spectral function is calculated, which actually matches very well what we see with one exception, which is the zero Landau level, which is there in the calculation, is not there in the data. How do we understand that? Well, here is where we have to look at the master. So the model being used for the analysis of the data is shown here, tight binding model, nearest neighbor hopping. What strain does is really renormalizing the hopping parameters in the system. So that's how we capture the strain. But now things are interesting if we go and add a mass term. And so the mass term is basically the symmetry breaking Semenoff mass term is coming from the interaction between the graphene and the substrate itself. And what happens then is that you have additional term M into your spectrum. And now this term M will, as you can see, is particularly strong in terms of its effect when you're looking at the zero Landau level, which really can be written this way. So really the zero Landau level would be pushed down or pushed up, depending on whether the mass term is negative or positive. And this is the largest effect you can see. The other Landau levels are also affected, but only to a smaller degree. Compared to what we heard today, one caveat here is this is not a real magnetic field. This is a pseudomagnetic field in that it doesn't break time reversal symmetry. And so the effect of M is the same on both K and K prime. This is something to be kept in mind. Okay, how do we then understand the spectra when we introduce a mass term? We can look now again at the figure I showed you before, where we have a mass term there, sorry, the zero Landau level there, no mass term. Then we can put a negative mass term, and you can see that the zero Landau level is pushed down below the zero point. And for a positive, you see the opposite. One little feature I'd like to highlight is this one. So there is also a zero level there, up above the zero point. And this is because you have one single monolayer of graphene going over these trenches. You have a certain strain that we postulate here at this stage on the trenches, but then the system has to go back. And so there is an inverse strain, thank you, at the edges of this triangle. So really you have two forms of strain together, the one in the middle of the trenches and the one at the edges of the trenches. And that's, of course, a weaker contribution, but it's also there. So the main one, though, is down here or up there. Now, of course, the way that we were able to understand why we don't see the zero level at all is if we assume a distribution of mass terms over the sample, distribution that can be, such that once you go and measure with photon emission and 1 millimeter spot, you average over all of those. And so effectively, you wash out the zero Landau level everywhere. And so that's how we explain how we understand the data here. As for the sample, a little bit more detail on the substrate. Indeed, these trenches are there. You can do detailed STM and AFM studies. You can show that the steps are really of one layer of silicon carbide. You can show doing adhesion AFM measurements that the monolayer graphene is covering everything very uniformly without breaking. And you can also do STM inside the trenches, and you can compare the STM done inside versus the one outside. And eventually you can extract an image for the strain. This is work done by Sarah Burke at UBC. And from that, in fact, you can show that the strain are consistent with what actually was postulated initially is the 3% strain that we have on the sample. So interestingly, the calculations were done before the experiments, and these confirm what we were seeing. For the coverage, 5 to 10% of the sample is covered by trenches. The size of the trench is regulated by the argon flow during the cleaning of the silicon carbide. And the trenches themselves are more of the order of 300 nanometers, where we assume 56 and 30 for the uniform fields that we have. The last couple of minutes, actually, sorry, before going that, this of course was done with strain, but more or less at the same time, this also came out, which is now black phosphorus, so graphene black phosphorus. So now we're going to go back to the engineering done by stacking, and so heterostructure, and you see similar behavior. So interestingly, it just came out about the same time. The difference here is that we only see the levels above the zero point and not so much below the zero point, while in the STM you can actually see them. And our interpretation is because the spectral function is broadened out very strongly as we go down below the zero point. And so presumably that's why we are not able to see these features, which are weak to start even in above the zero point. The last point of the talk, the last couple of minutes, is on the last way. So the last way is to now do, after we've done the, doping the system to induce superconductivity by really altering the electron photon coupling, and then looking at substrate effects, go back to the idea of adatoms, but in a very dilute limit. So, and now we look at defect-induced instabilities in graphene, and in particular, formation of a bond density wave into the system induced by an extremely low level of impurities, lithium again, on the surface. And so graphene has all kinds of possible order that have been brought up. An interesting one is this one, is the Kekulé bond order, where you have modulation of the hopping parameters, again, along the bonds. So then you have, strong bonds and weaker bonds. And this leads to a larger unit cell, square root of free, rotated by 30 degrees. And effectively, if you look at what happens at the electronic structure, now K and K prime, Dirac cone are all folded down to the gamma point, now become equivalent, and a gap opens up. So the idea is, can we now, after we have done the Landau level over entire crystal, also generate a density wave order, which really has not been observed very much into this system, or gain over the entire crystal by small amounts of defects. And the two key signatures are the folding and the gap opening. So here is the sample again, is our Dirac point at the K point. Here you already see that things don't line up very well, the upper and lower part of the Dirac cone. This is again the effect of the mass turn that gives you a bit of a gap where the Dirac point would be. But the question is what happens as we dope. And in this case, we deposit a 0.3% lithium coverage. This is about sort of 100 times smaller than the max we've done in the previous case where we go to superconductivity. So it's an extremely small amount, to the point that we don't see any doping effect. And as we do that, though, the key is that now we see folding of electronic structures. So the Dirac point that you see here has been now measured at the gamma point, and is really the result of K and K prime folding down there. And what is interesting here, so this is the first of the signature, folding of electronic structure with an extremely small amount of impurities. And now the question is there a gap getting larger? The gap is already there, but is a gap getting larger at the Dirac point itself? And yes, it is. The gap is now two contributions, one coming from the folding and the other one coming from the mass turn. And it's basically an enhancement of about 20 to 30% of that gap. And so we extracted a 2 delta K. So due to the bond order is of the order of 200 MeV. So that's basically what we see. Now, we can also look at structural information, so electron energy loss. And here there is a figure. I'm not sure if all of the different spots show up, but you can see, you can see the graphene original, the pristine. You can see the silicon carbide. You can see the superstructure due to that. But in blue, you also see what comes from the lithium. So again, the folding due to lithium, and you can see here in the line cut across all these data points is that by putting small amount of lithium, nothing really changes. Sharpness of peak stays the same. What really is the new information is new peaks due to the folding of the structure corresponding to the bond order. Now, the way we understand it is the following. So we wanted to establish this particular phase. We come in with the lithium adatom on the surface. Immediately you get into a situation of Friedel oscillation induced by the lithium adatom. Now a second lithium adatom could come in and could end up on a different location, which is not in phase with the fermion one. However, if the deposition is low enough, if the temperature is not, is high enough to allow for some kinematic on that surface, then the second impurity would also align itself in phase with the previous one. And so it would be another one that you put in. And eventually you get a long range order coherent phase on the old crystal. And so in fact, by doing both the experiment and the simulation, we can confirm there's low lithium deposition, give you that long range order that you would like. The order is of Kekulé type, so bond order over the entire sample. Fast deposition, basically you get only order on a few sites and immediately go in a frustrated type situation. Working high TC, high temperature, then the mobility is too high of a lithium atom. Again, you get into, you're not able to establish a longer order. So really you need a combination of very slow deposition at temperature which are low enough to be able, but intermediate, let's say, to be able to establish this very long coherent type of order. With this, I'd like to just mention again that, this was work done at UBC. Very important contribution from 3 students who led the 3 different projects: Pascal, Bart, and Amy, and Christopher Gutierrez, who's now a faculty member at UCLA. Theory, Marcel Franz and Etienne. We have had work with Doug Bond and Sarah Burke as far as the STM, and the sample were coming from the MPI Stuttgart, in particular Uli Starker work. And so concluding 3 ways of really looking at new quantum phases in monolayer graphene, but in this case on silicon carbide. Superconductivity, not through twisting, but through a lithium superstructure at large levels of doping. On the opposite limit, very dilute lithium concentration, you can now induce the long-range Kekulé order, bond order on the system. And through the substrate, pseudomagnetic field large enough to give you a macroscopic set of Landau levels on a wafer size scale all the way to room temperature. And with this, I'd like to thank you. Yes.
Is that the case, or is like choosing some just to maintain these clubs? What makes the fidelity being in phase or out of?
Well, so this is the most favorable location for the lithium to go in and sit. So this is based on a combination of so we don't have we have a circumstantial evidence when it comes to the overall picture, but otherwise it's mostly based on DFT arguments that's where it would go. And then when it goes into the second one comes in, well, this is basically nucleate a potential landscape under that, and so now this potential landscape through the Friedel oscillation is transferred to the neighboring, let's say, region. The distance between these lithium atoms is of the order 2 nanometers. So you're looking at quite a well-separated lithium impurities. And so it's what we see is experimentally is using temperature. Now we start with deposition, and then we start getting these signatures of order, and then we go up a little bit in temperature, and then you see that everything gets sharper. So somehow by using temperature, a few Kelvin, as a way to modulate the kinetic of a system and slowing down the deposition, then you can, and so then the suggestion is that, yeah, it is a long range order, and the only way we're able to build it is if these are indeed in phase on the same registry. The opposite is really very intense deposition, or going too high in temperature, eventually everything goes away. Everything goes away. There's a question back there, I think.
So this dilute lithium is the lithium atom doping effect of lithium atom ignored. But what about silicon carbide? It also dope the.
Sorry. So the same, with dilute case, we don't see doping of lithium into the graphene, right? And you're asking what happens below?
Yeah. So the silicon carbide is still doped.
It's not doped by lithium. Right? So basically, with silicon carbide doesn't contribute anything as far as the electronic structure and the chemical potential. This is, what you see. All you see there is graphene itself, right? So.
Way to get rid of the dope silicon carbide.
Itself. Well, so yes, if I have a second, I can show you. How do I go? Oh, here. Is it too difficult to jump forward a few slides? Yeah, it's just I have to click randomly over a lot of stuff. Okay, thank you. I think you're asking about this. And can we go back to current? No. Yeah, it is. So basically that's your question.
Yeah.
So the way to change the doping, because really the question was, is this due to nesting, or is it due to something else? Right? That was the question that I think you were going to. And so the way we did it was to look at different system where you now you're looking at graphene, and then you have hydrogen intercalation, or you have gadolinium intercalation. So different forms of intercalation, and in one case you can get excessive doping over this, even larger doping. But the other one, now you can p-dope the system. And in fact, we see exactly the same effect on all of them. So basically, independently of the doping of a graphene, we are able to see the same long-range order induced by those small amount of lithium. And so that tells you that it's nothing to do with nesting. It's really not nesting. And so then, even though the Friedel oscillation picture is something that we can use to understand how the lithium would go and organize themselves, basically self-organize themselves in a way which is coherent, when it comes to what gives you the folding and so on, is really not the outcome of pure nesting instability. It's more like into electron funnel, strong coupling type scenarios that I would imagine. So doping certainly allows you to reach the same result everywhere. And you can actually look at things like, at the gamma point, you can see that you have K and K prime coming to the gamma point, giving you very specific shape for the gamma point. Yeah. Yes.
So, do you expect any activated disclosure in that kind of sample? And if so, do you have any comments about its relation to
So there was one key difference there. First of all, these operations were done very fast, not a low temperature. Everything was a low temperature because mobility is a problem, but really fast, really high deposition rates. And to the point that we have here, if you look here, you see that there is a folded band, but there is also a lithium band. So they are two completely different regimes. So in this case, I would say that I would exclude that you have a well-organized Kekulé. If we look at lead, we don't see a well-defined pattern coming from the lithium. So it's quite messy and quite disordered. So it's really two very different regimes, The biggest effect here, I think, in terms of induced superconductivity, following the work of Profeta, is really the different quantum confinement of wave functions and introducing lithium phonons into the problem. So it's really a different origin. Now what we're trying to do, though, is go back to the very dilute and go up from there. So that's what we're trying to do. Yes, and Christopher at UCLA is trying to do that with STM. So to really combine the two pictures, real space and momentum space. Yeah.
So I don't know about the Landau level part. So I'm wondering, is that possible to change the shape of the punch into hexagon instead of triangle? The reason I ask is because the triangle shape is introduce mass for the device. So in principle, hexagon preserves 6-fold symmetry should suppress the mass, and it's possible to give you the dynamic zeros Landau level. So I'm wondering if that's possible.
I think so. I would say is highly unlikely. I mean, I can tell you an anecdote after, but basically, if you really look at this object, really the system likes to have those defects, right? They are all triangular, comparable size. It's a distribution in size, but very well centered, around 300 nanometers, and it's just one monolayer of defects, and this happens during the growth. Now, how would you go into an hexagonal type shape? I have no idea. How would you first force the system to do that? But you could imagine of having now, especially with better microfabrication approaches, to have, instead of something that happens during the cleaning of the silicon carbide, have trenches of a certain shape put down and now grow graphene on top of that. That's certainly something that one could do.
In this shape, I think the totally agree with the observation about the mass. This shape is proximity point with the mass.
So the anecdote that I want to say is that, we did the experiment, we recognized that there were features that you couldn't explain as anything else, no bilayer, trilayer splitting, they are different, cannot be electron phonon. So then we started looking with Marcel and his student Etienne in the idea that you had strain. We knew that the symmetry had to be trigonal of some kind from Guinea's work. So that's what we started looking for. And so we did all the work, came up with the size of the trenches, the field it would establish, and then we did the STM and found them. So it was reverse, the process. Yeah. Thank you.
Thanks.